Hi. This is going to be the last concept of struggle materials. What is the buckling phenomena of losing the stability? At the beginning, we said first, the object of struggle materials is a rod, a system of rods. The second, what do we do with this rod? We calculate it in strength, stiffness, and stability. Strength, stiffness, or stability. You forget everything about it, but please do not forget these concepts because they are very important. They are a core of our profession. To calculate in strength means that to guarantee that my rod is not going to have to break or to have permanent deformation. To calculate in stiffness means that my rod or the system of rods won't have deformations bigger than the one for normal operations. I mean elastic deformation, because if the rod has plastic deformation, it means that lost is what? It's strength. So please do not confuse strength with stiffness. Once again, calculated strength means that my rod is guaranteed either not to break, if it is breakable material, or not to have plastic deformation, if it is a plastic material. To calculate its stiffness, or sometimes we call it rigidity, means that my rod does not have excessive deformations. It doesn't matter if there are elastic deformation, if there are excessive deformation, can cause other problems or not the normal functioning. Even if it is a structure, is a bridge, cannot deform that much. The bridge is safe, but the train is going to fall. Or a shaft. The shaft is not broken, but it's going to cause noise, to burn the bearings, to break the gears, and so on. The third concept is the concept of stability. The concept of stability comes with the concept of equilibrium. And I'm going to give a very simple demonstration, the one that you had before in physics. Look here, I have this sphere here in top of this platform. This one is in equilibrium. I have the same sphere or ball or cylinder, it doesn't matter. This one is in equilibrium as well. And I have the third position is this ball or sphere, and all the three are in equilibrium. What's the difference? The difference is if I push this one a little bit, it's going to come out from the position of equilibrium and never to come back again. So this is called unstable equilibrium. If I push it a little bit, it's going to come out from the position of equilibrium, but it's going to come back after many shakes. This is called stable equilibrium. And this one, if I push it a little bit, is going to move here from one status of equilibrium to another status of equilibrium, but it's the same. This one is called neutral equilibrium. Sometimes we call it indifferent equilibrium. So stable, non-stable, indifferent. In many other books, you have seen this concept by a body rotating about an axle. This is the axle of rotation. You see, it's the same body. Now this is the axle of rotation. And it's the same ugly body, potato, and this is the axle of rotation. This is the centroid, the center of gravity of this body, this one, and this one. So now the first one, if I push a little bit, is going to go from this equilibrium and never to come back again. Unstable equilibrium. This one is going to shake, but come back again. Stable equilibrium. And this one is going to rotate, go in another position of equilibrium, indifferent or neutral equilibrium. What this one has to do with our object, with the rod, because stereo materials studies rods. I'm going to clean it. The problem of stability or buckling does not happen all the time. Happens for certain structures or certain problems of structural materials. The easy one, the most common one, is this one. I have a short rod. If I pull it, what's going to happen? It's going to be deformed, pow, break. Now it's going to lose what? The solidity. If I push it, so the same rod, but it's a short rod. Remember at the classification, initial classification, we call a rod short when this length is shorter than 5 times the diameter or the cross section, 1 dimension of the cross section. If I push it, what's going to happen is going to be maybe deformed, or if it is amorphous materials break, but that's the way it's going to happen. It's going to have a limit until it's going to have permanent deformation or break completely. Now, if I have a long rod, theoretically should happen the same thing. So I push it until it breaks. But in practical, does not happen like this. What happens if I push it for certain times? This rod might come to this position. If I keep increasing this load, and if I decrease this load, the rod is going to come back to the initial position. So if I'll start from the force P and I go to the value P1, is going to lose the axle but come back in this position. Why this happens? We know why this happens. First of all, we don't know where is the center. We're going to put the force somewhere. But when I pull it, it's easier. Otherwise, I pull it from the center. Second, this axle, theoretically, we said that the axle is straight. In practice, it's not straight. There are many hypotheses, many lies we say in structural materials. So that's why sometimes, because the axle is not straight in here, this force might give a moment. Now, if I increase the force, I say it, to a certain point, it's going to go to this position, but if I decrease it, it's going to go back in that position. But it's going to be a value of the force, that if I increase it that much, the rod is not going to come in initial position. This one, this value here, guys, I'm going to give the name critical load. So this is a critical load. So if the load goes to that value, it loses the so-called stability. So what does it mean to lose the stability? To lose the shape and the status of stable or indifferent equilibrium. The status of stable or neutral equilibrium. And it happens in the buildings, it happens in the bridges, it happens in the high columns, it happens usually, sometimes we call them axial bending, because the pressure is to the axle, but still it's called bending. So losing the solidity, breaking, bow bow. Losing the rigidity means that too much deformations, elastic deformation, and losing the stability, losing the equilibrium, stable or indifferent. The problem of stability for the first time was caused by Euler. The problem of Euler you are going to have in the lecture. That's all you have to know. You have never should confuse this concept. Unfortunately, I see people in the everyday life, engineers, professionals, it's going to break, it's going to use the stability. You cannot say that. You cannot say. You say like an elephant has wings. You cannot say that the elephant has wings. Only the cartoons, in Disney cartoons, if you lose stability, lose the equilibrium. If you lose the rigidity, too many deformations, elastic. And of course, if you lose strength, it's breaking or having permanent deformation. That's it, guys. Maybe it's the last lecture dedicated to strength materials. Of course, we're going to refreshen up everything next year in the other disciplines of mechanics of solids to follow. Thank you.